base platform that we're using is the Arduino microprocessor. We've selected that one because it's very open source. There's a huge community of resources out there. There are a wide number of peripherals available that you can just plug into this thing and roll with. So it gives a lot of flexibility with limited knowledge. Sadly, none of those up here are engineers. So if we really had to get into hardcore coding or building on our own, learning a new coding system, anything like that, we'd kind of be dead in the water. This thing is very friendly. The original application for it was for art students to make clothing that lit up and glows and stuff like that, and then it eventually evolved into this. So I figure if a bunch of art students can handle it, so can we. Now, to incorporate our wireless aspect, you're going to have some kind of wireless radio. We went with the XD for pretty much the same reason we went with the Arduino. It's open source, there's a good community of support out there, it's very easy to use, and there's a shield that lets you plug it right into the Arduino with no muss, no fuss. It just rolls on and works. It also uses the Zigbee protocol, which is a very handy underlying software protocol for wireless networking that has already been developed, it already exists. There's a huge number of libraries out there for it. It is very reliable, it's ad hoc, so you can plug and play different things into it and it'll just keep rolling. Very versatile, hard to screw up, that's good for us. Now, in order for us to get any sort of data, we're going to have some kind of probe. So we last year actually looked into what are some of the most important aspects of water quality that we could test. The three things we came up with were pH, dissolved oxygen, and temperature. So we started fishing around looking for probes that we could use. There's a company called Atlas that makes a wide range of probes. They're relatively inexpensive. They are pretty robust, fairly easy to use, and they supply code so that you can just drop them onto an Arduino board, download the code, and start rolling. Very handy, nice to use. We continued on with that this year. The red one is pH, the yellow one is dissolved oxygen or DO, and then the thermistor at the bottom is what we're using for temperature. So, individually, each of these probes is actually fantastic. You just plug them in, they start taking readings, they're pretty easy to calibrate, they give you the code for how to do that, plug them into standards, get going, no problems, until you try to run more than one of them at a time. The problem with these probes is that they use voltage for everything. So they pump the voltage into the water, they watch it drop or rise depending on what it's testing for, and they convert that difference in voltage into whatever reading you're going to get. Pretty straightforward, very common, doesn't seem like it should be a problem. Until you put two things next to each other that are dumping voltage into the water, and then things start to get screwed up. Now the biggest problem with these guys is that they're in an always-on configuration. If they are plugged in and getting power to the board, that probe is dumping power. Even if you're not reading right then, it's still dumping power. That took us a while to figure out. So there's not really a software solution where you can say, okay, just don't read continuously, problem solved. So we tried that, didn't work. You actually have to isolate the probes using hardware. So you gotta have some kind of switch. You gotta have something in there to break the power stream to turn off the probe, otherwise it just keeps going. So we did not come up with this. This is Yusheng's baby, and it is magical. This is a lot cleaner than we had last year. He printed a PCB board for us. Made soldering way easier, no big hairy tracks that get screwed up and touch one place in a tiny little spot and short the whole thing out that you don't notice, and you let the magic smoke out. Last year was a little bit of a hassle. This year, much better. But there are two different aspects of how we're actually breaking up the power. On the analog side, we're using a transformer, so you've got induction, so that power is never directly touching, so you can shut it on and off by flipping the transformer. On the digital side, we have photocouplers. So they're never actually connected by solder. There's no direct link. It is an on or off based on the high-low output of a really tiny LED that's inside this little speck of a chip that we soldered to the bottom of the board, and there's 4 of those scattered out. But that was our solution, since you can't really break that wire with a switch fast enough to actually make this work. Photocouplers, the speed of light, no switch is going to be able to go quite that quick, so beautiful solution. Thank you, Ishi.
And I would just like to say that mine worked, whereas he had to work on theirs for a long period of time.
Last one done, first one finished. Okay. This is some sample data, because we actually did deploy this system in a controlled lab environment the other day, which means we dropped them all in a fish tank and left them overnight. We started out with the water slightly warm out of the tap, left it sitting in an air conditioning unit, so overnight it started to cool down, which is what you're seeing with this yellow line. The blue line is our pH. There were no fish, there were no plants, there was nothing in there but water. So realistically, there's absolutely no reason why the pH should change, and it did not. So that's excellent. DO had some weird spikes. We're not real sure why, because again, no fish, no plants. It shouldn't have changed much. And if we did see a change, it should have been a slight decrease over time as oxygen bubbled out. That is not what we saw. It's really pretty much a flat line whenever you drill in, but this is something like 12 or 15,000 data points. So the DO data is a little bit dirty. We're going to be looking at ways to clean that up and figure out why we're getting so much flux. It's really within alpha, so it's not bad as far as what it's collecting. You could use this data effectively in a research paper, for instance, without any problem, but it doesn't look real nice. And so we're going to see what we can do to fix that.
Just for clarification, is that each about an hour long?
8 seconds. So it's taking readings every 8 seconds on pH, DO, and temperature from 5 different sensor clusters.
So I guess I'll ask later about the curve on the top.
Next slide, because here we go. So how that data, the hardware collected, get to the graph? Not real straightforward. There's kind of a couple things that go into it, and that's where Mike's going to step in.
Okay. So I focus mainly on the software side of things. Basically, with the Arduino, you have to have a code that tells you what to do. You don't just plug it into a machine, drop the sensors in, and magically get a graph. So what we got, our code is basically saying, I want to take these 3 sensors that I'm plugging into these ports on the Arduino. We want to supply power to those ports to make the sensor read. Again, like we said, the 3 sensors we use, pH, DO, and temperature. And our code basically says, take the temperature reading, take the pH reading, take DO reading, finish. Start again. And we have it set to run every 8 seconds. So that graph that we just had, like you said, like 16,000 data points over a 24-hour period. We're collecting a lot of data. In order to transmit the data, we went ahead and packaged it all in one. Also, with the way the software works, you can't just say, take a pH, send it. Take a DO, send it. Take a temperature, send it. So we went ahead and packaged it all together into one string. So what we would see as our printed data, we would see that we have a long string here that is 14 characters long. The first 2 characters that are printed represent the node. Since we're making a wireless sensor network, we will have 5 different nodes that are all going to be sending data. We need to know who's sending the data, where it's actually coming from. Otherwise, we just have a bunch of numbers. So the first 2 characters represent the node. The remaining 12 are the pH, DO, and temperature values. And I'm going to show you how that breaks down here. First 4 in the next, right here, these 4 digits here represent our pH.